So next, let's look at page 221 and subsection 1.3 concerning work. Now the work is from physics that you might remember is some force. There's a field where there's a force influence, such as maybe gravity or something, and then there's a particle moving along some curve along the field. Okay, to calculate the work that is done, well, the field, then we first consider the field as the force field as having x and y components. The x will be big X of xy, and y and the big Y xy, which are the x and y components of the force. Now the magnitude of the force is of course the Pythagoras theorem, square root of x squared plus y squared, and being that the force is a vector. And so then the direction then is also given by a tangent inverse of y over x. Now the force in physics is defined as force times distance. That is, you apply a force and how far did you travel applying that force, dragging it along, and that's counted as work in physics. So normally it's counted as force times distance, but that's only if force and distance are going in the same direction. If your force is applied at an angle, then in physics, then the work done is counted as the force cosine theta. In other words, the component that's along the path. Okay, so the work done then is force cosine theta times L, because only the part that's along the path of the force matters. Now, so next, let's if force times distance is particle moving a straight line through a distance L under a constant force in the same direction. So then what if we're traveling on a curve? Then we'll define as always that t goes from A to B, and then we'll cut it into tiny little bits from T1 to Tn, right? And then the arc length of the curve between these points, we'll call it delta S, okay? And we're going to be dealing with arc length in this situation. So theta is the direction between the direction of the force of the field at the point t0. So here's a random point t0 in the line of motion, and here's a force. And let's see. The point is, this is theta I. Okay, that's the, well, I'm missing an I there, but this is the angle that the force is making with the tangent. And then we are going to, let's see, okay, the work done then, of course, is equal to the force, okay, times cosine theta times distance traveled, as we see here. And in this case, the force is the magnitude of the force times cosine theta. That will give it the magnitude of the force in the direction of the traveling. That is tangent. And then the delta S is the distance traveled. And then we'll add it all up, okay, in the limits, in the summation. And then we'll calculate the limit by forcing the subdivision into 0. And that whole thing, all that will add up to become the work done through some curve. All right. So the directional components are in this definition. X, the big X function will be x. Small x will be defined as phi of t, and big X is the psi of t, like this. Okay. And then the force function is defined as x of xy before. And then we'll substitute the x equal to phi of t, y equal to phi of t in there in this function. And similarly for the y component the same way. So x is from now on parameterized only, we're considering only along the curve where x is phi of t and y is psi of t. The direction then, of course, are the derivatives of phi of t and psi of t, as we learned in the vector section. Okay, it just is. Okay, don't even think too much about that. And so that's the direction. That is the tangent. The tangent component is that. Okay, so in other words, the tangent is the tangent vector is parentheses phi prime psi prime of both of t, and so then. Well, what we have next is this formula What formula? Okay, so what is cosine theta I? The cosine theta I is given by this formula, like right here. Now, where did this formula come from? This formula is the dot product of x and y here, and dotted with the tangent vector, this one, okay? And then divided by both their magnitudes. In other words, the big X, big Y vector is being dotted with a tangent, which is phi prime psi prime. It gives this thing. And that comes directly from the formula that we have used many times, okay? This is the formula cosine theta, and that's what we're doing here. Cosine theta is the two vectors r dot s divided by their magnitudes. So that's exactly what we're doing here. So this looks more complicated, but the idea is exactly the same for cosine theta. Okay, so that is cosine theta. Next, what is delta S? Delta S is given by this formula, and this is from page 89, which I want to show you that again. Okay, here's from page 89. The arc length, okay, is given by the Pythagoras theorem, and you integrate. Well, of course, in our case, we only have two dimensions. We don't have the third one, but the idea is the same. And this is on page 89. So that's where we got the formula for delta S. And so the next thing we're gonna do is, out of this formula, we're gonna yank out phi prime and psi prime. And the square root, okay? We're going to yank the whole thing out by the mean value theorem on page 9. And just so then we only have delta t left. So the entire integral got yanked out into this thing where psi, the psi will be something between the ti and ti minus 1. All right, so far so good. So we have a bunch of stuff. So now let's write it all together, which the book has not bothered. So I have it written down right here. Now, as you notice, this is the original formula, okay? And this is the x squared I plus y squared I, the first part. And then the cosine theta is this part and divided by this and that. I wrote this one and that over here for a reason, because they're the same up and down here, okay? So we can cancel them out. But this part stays. That's the cosine theta part, okay? Plus this thing, and if you check, and then and this part is the delta S. Okay, there's the delta S, which becomes this plus the delta T, of course. So if you check this, then you notice that I have all parts accounted for. Okay, just plugged in. That is, I just plugged in these formulas into. I plugged in these formulas. What is cosine? Plugged cosine theta in here and plugged delta S in here, and just rewrite this thing with which turn into that and that. Okay, so please do this yourself too. Okay, and because that's the fun part of studying math, is getting it to come out exactly. So now that we have this is a big this part cancels, which is fine. But what about the rest of it? The rest of it, we are going to consider this f of ti, okay, that thing that I circled in green. And the thing I circled in purple, or whatever that color is, that we'll call that g of psi I. For what? For in Duhamel's theorem on page 173. That is right here. Here's Duhamel's theorem on page 173. Right there, okay? And what does it say? That says this limit is going to be equal to this. That is, you have two different variables, psi k and eta k in here, but that don't hurt nothing, okay? It all converges, it all turns into the same function in the integral. So that's what we're going to do. So it's a very handy theorem. So here's Duhamel's. All right, we have. Why is my camera not focusing? There it is. So then the f here, okay, and the g here all collapse into the same variable. Okay, we'll call it dt. So this thing, so f turn into that, and right, and we don't worry about what's on the inside because they all come out to be the same. If that's the case, then well, these things are already canceled out, so we just have this thing left, and this, and now they have the same variable inside. This can cancel with that. So we only have this left. Now, isn't that magical? This big, long, complicated thing got turned into this thing, okay? And so the next step we do is that, what about this thing? This thing is, well, the first part is we can, is big X phi of phi d. This is phi prime. This isn't just phi, okay? There's a prime there. My prime looks kind of ugly, but it's a prime there. So this is a phi prime. Now phi prime dt, phi is a function of t. Phi prime dt, as we given, it was is x. That is dx, okay? Because x is phi. So phi prime dt t equals to x. Equals to dx. Similarly, psi prime dt equals to dy. So this equation then got turned into the integral along the curve that we're talking about, and with big x dx and plus big y dy, as the book shows. Okay, that is how we got to this point right here. See, is you just have to write this whole thing out, okay, and apply it to Duhamel's theorem carefully, and this will come out. You see, the book hasn't bothered to do that because it is the responsibility of the student to write out all the details. So that's how we got this part, and that will be the work done of some. What have we been doing? We're doing the work done of something going along a curve. And whereas big X and big Y is the force field, okay? And tau represents the curve that is traveling through. And tau is being represented by phi t, X equal to phi t and Y equal to psi t. So that all comes out nicely. So please go over this yourself. Make sure that everything makes perfect sense, all right? So next, let's look at page 222 on the next page, where we have an example. Okay, so let's consider the example. If we have big X is equal to a simple function, small x plus y, big Y is small x minus y, and then our particle is moving from 1, 0 to 0, 1. That is, down here. Well, we don't really care how it moves, okay? It just moves that way. And then we need to calculate the work done. So that's what we did here. Let's see, where's my, can't find it. What's this? Oh, the other, on the back page. All right, so here is what I have written down. We have big X equal to X plus Y, big Y equal to X minus Y, and more importantly, we have X equal to phi t, Y equal to psi t, such that when t is 0, then phi is 1 and psi is 0, okay? Because we're traveling from 0, 1 to 1, 0 or something like that. Similarly, when t is 1, then phi is 0 and psi is 1. So they sort of reversed, which is fine. And now let's write down the integration just like it says. We're applying that formula there. So plugging in small x and small y, excuse me here. Plugging in small x and small y, we got this formula. We have phi, and then and this is the phi plus, okay, let's see, wait for my why is my camera not focusing? There it is. Okay, so we have phi plus psi, that's the x plus y, times dx, okay? Dx is phi prime t dt. And then the other part is similar with x minus y and stuff, and dy. So that is that's fine. And now we can actually integrate this thing without knowing what phi and psi are. That's because we have phi times phi prime t dt. That integrates to be phi squared over 2. Okay. And similarly over here we have a psi minus psi prime t dt. That integrates to be psi squared t over 2. And the last part is we have phi psi prime plus phi, what am I saying? No, this is pronounced psi phi prime plus phi psi prime. Okay, in other words, that's the result of the product rule. That is, if you differentiate this thing, It will equal to those two things I just tried to pronounce. So we have all things integrated without knowing what these things are. And now that we integrate it, we evaluate them at the endpoints. We already know what the endpoints are given here, right? When t is 0 and etc. So evaluating at those values, we get -1. And you notice that we got -1 regardless of what phi and psi are. So then we don't care how that is. Phi and psi represent the exact path that goes from 1 0 to 0 1. But the exact path doesn't matter. No matter how you parameterize phi and psi, it will end up the work done will be the same. Okay, it will be -1. So that is the point of this example, and so on. So you should mention that the field is called conservative if the work done is independent of path, but we're not. I'm not that interested in that. So please read the rest of the little paragraph yourself. Okay, some comments on physics, conservative and stuff, and we will do homework. So for homework, please do page 222. Right? Yes. 222. Please do problems 1, 2, 4, 7, 8, 13, and 14. And when you get back, I want to talk about them. So first, let's look at problem 1. Not much to say really. We just do some calculation just like in basic calculus, and everything will come out nicely. That's that's about it. So that's problem 1, the same as problem 2. You just crank it out, and then problem 4, same thing. Let's see, okay, maybe like that. So you just follow the curve tau gamma, okay, and then calculate each part until everything comes out, I guess. And then problem 7 is the same as the example on top of the page 222. You're doing the same trick there, where the integration is can be done without knowing what phi and psi are. Okay, so I wrote the same thing down here. You're doing anyway. So that's that. So next, let's look at problem 8. Something about the force is the inverse squared of something, which is fine, okay? So I'll write down the force is the inverse squared. I put a negative sign there because, did it say attraction or something? I guess I'm assuming that it's attracting. And maybe it isn't, who knows. But the negative sign isn't critical. It's just the direction that it's pointing at. I'm assuming that is pointing back to the origin or something. Anyway, but like I said, that's not that big a deal. So then we have the big x is the cosine theta, and the big y function will be the sine theta. And where x and y are parameterized by cosine and sine, as always does. So then when we plug in the work done formula according to the book, then you don't have to do much. You just take a look at this formula and you realize quickly that it equals to 0 somehow. Cosine, sine, cosine, sine, sine, cosine. See? And then there's a negative sign here, so it all goes to 0. And the reason the force is 0 is because the force is perpendicular to the path of the to the motion, so it is not doing any work. Now, did it say that? Yeah, work done over path example A. That's because example A is a circle. Okay, you're going around, so you're not doing anything. So this is similar to swinging the planets doing a circular orbit. It just goes around forever because it's not doing any work. So that's that. Next, let's look at problem 13, where the question is, what happens when the fraction, the denominator, when in fact the fraction is phi prime and psi prime are both 0. Okay, well, it's such as in the case of t squared and t third, which looks like this. Well, if it looks like this, we'll just integrate up to the point where stuff is 0 and then keep integrating. Just integrate in 2 chunks. That should do it, I would think. So that is that. And next, let's look at problem 14, where we have two functions. One's continuous, the other one, g, is in C1. And so we need to calculate that limit. Okay, so we'll calculate the limit. I have the function written down right here. Okay, and so here's the function. We're going to, what are we going to do with this thing? We're going to apply MVT on page 46, because that one has two variables. So like that one looks like this thing, okay? After you apply that MVT, then you will get something like this all the way through. That is, you have partial derivative, first partial derivative, and second partial derivative. And I will show you page 46 to, is it 46? Yes, it is 46, okay? That we did some time ago. See, this is the MVT I'm talking about. You have in two variables, okay, you minus AB, that will be F1 of something plus F2 of something. F1 and F2 are the first and second partial derivatives. So once we plug that in, and then the next step is we're going to turn the x's, okay? And the xi is equal to phi of t, and the y is equal to psi of t. So the x's, we're going to apply the one-dimensional MVT and turn it in. The difference then becomes phi primed and delta t, and the other difference becomes a psi prime of delta t of some t in there. So then the entire integral, now we're going to apply Duhamel's theorem. There are various, there are two or maybe more. I don't know how many, I think they're just two. Let's see, yeah, I think they're just two. How many variables in here? Let's say there are two variables in there. Should there be more? I'm not sure, but anyway, my point is we're just going to apply Duhamel's theorem, and so everything will come out to be the same, okay? And then we don't have to worry about which t is talking about. And once we apply that, then the thing cleans up to look like this one, d phi. Well, phi is just x, or in the other representation, it will look like this. So finally the limit will approach this thing right here. That's my final answer, okay? And that's it. And that should be the end of this section.